Welcome back to the Energy Conversion Lectures. In this lecture and a couple following lectures, I will review and discuss some important mathematical relationships that are used for analyzing and solving the magnetic circuits. The first important mathematical relationship is Ampere's law, or IH relationship. We learned from the previous lecture that current carrying conductor produces a magnetic field around it and its direction determined by the right-hand rule. The intensity or the strength of this magnetic field is denoted by the letter H, and its unit is amperes turns over meter, or in SI unit just ampere over meter, because turns is not SI unit. Ampere's law stated that the line integral of magnetic field intensity H along a closed path equals the total enclosed current. The formula of Ampere's law is a closed path integral of H dl equal the sum of the current enclosed by the closed path. Basically, if we have a closed loop path of magnetic field intensity H produced by currents carrying conductors and take a small element HdL, where dl is the length of the element, and then integrate that element along a closed path, the result will be the total current enclosed. For more clarity, we can shade the area surrounding by the closed loop path to identify the enclosed currents. Let's have a small example. If we have two conductors, the first conductor carrying 7 amperes and the second conductor carrying 2 amperes. These two conductors producing magnetic field intensity H around them in the direction shown. If the total length of the magnetic field is L, the magnetic field intensity can be determined based on Ampere's law as follows. First, let's shade the area enclosed by the magnetic field path, then write Ampere's law. Closed loop integral of H times dl equals summation of enclosed current I. Since the total length of the magnetic path is L, therefore the integration of the element HdL along the closed path will be equal to H times L. This will equal to the sum of the enclosed current, which is I1 plus I2. The mathematical signs of the currents are determined based on the right-hand rule and will be positive sign if the current direction is matching the right-hand rule, and negative sign if the current direction opposes the right-hand rule. Therefore, the result will be H times L equal positive 7, negative 2 equals 5. Therefore, H will be equal to 5 over L, and the unit is amperes over meter. Now let's apply Ampere's law to the following magnetic circuit. In order to apply Ampere's law to this magnetic circuit, we need to make some assumptions. The first assumption is that all magnetic field lines are confined to the magnetic material or the medium. In other words, all magnetic field lines flowing inside the magnetic material, and no magnetic field line leaks out of the magnetic material. However, in practice, there are some magnetic field lines leakage flows out of the magnetic material. So to simplify the calculation, leakage lines will be ignored at this point. The second assumption is that the magnetic field lines are uniformly distributed in the medium. In actual magnetic circuit, it is very hard to get uniformly distributed lines. For instance, the distribution of the magnetic field at the corner could be different from the center of this core. However, the assumption of the uniformly distributed magnetic field can give acceptable results close to the actual distribution. Based on these two assumptions, the total magnetic field lines crossing the cross-section area A of this magnetic circuit can be calculated by integrating the magnetic field density over the total cross-section area. In more details, if we integrate a small element of BdA over all cross-section area A, the result will be as follows. Phi equal integral BdA equal BA, and the unit is Weber. So in this equation, phi will represent the total or the sum of all magnetic field lines that flow through the magnetic material of the circuit. Also, B will represent the total magnetic field density. After all these assumptions, all magnetic field lines could be represented by one magnetic field line at the mean or average path of the magnetic circuit. Now, if we assume that the length of the mean path is equal to LC, we can apply Ampere's law by first shading the area enclosed by the magnetic field closed path LC. The total current will be equal to the sum of all conductor currents enclosed. In this case, each turns of the coil carry a current and enters the shaded area. In this example, we have 4 conductors carrying current, which equals to the number of turns of the coil. Therefore, Ampere's law can be applied to this magnetic circuit to determine the magnetic field intensity as follows. It is very clear from this equation that the magnetic field intensity H is directly proportional to the number of turns of the coil N and the amount of the excitation current I, and inversely proportional to the length of the magnetic path LC. The turns Ni is called Ampere's turns of the coil, which is also called magnetomotive force MMF, and denoted by capital letter F. The MMF in magnetic circuit is like the EMF or E voltage source of an electric circuit. The EMF E drives the current I through an electric circuit, and the MMF drives the magnetic field lines phi through a magnetic circuit. Now let's apply Ampere's law to a magnetic circuit that have 2 mediums, magnetic material and air gap. Also, let's apply again the 2 assumptions mentioned before. The first assumption is that all magnetic field lines are confined to the medium, and the second assumption is that the magnetic field lines are uniformly distributed within the mediums. Based on these 2 assumptions, the magnetic field lines phi and the magnetic field density B within the magnetic material and the air mediums are equal. However, it should be noted here that the air medium has much higher reluctance to the magnetic field lines comparing with magnetic material. The reluctance to magnetic field lines of a magnetic circuit is equivalent to the concept of resistance to electrical current of an electrical circuit. To keep same magnetic field lines in these two mediums, the magnetic field intensity of the air medium will be different from the magnetic field intensity of the magnetic material. I will talk about this concept in details later in the future lectures. Now, if the magnetic field intensity of the air is denoted by Hg and the magnetic field intensity of the magnetic material is denoted by Hc, Ampere's law can be applied to this magnetic circuit as follows. Based on this result, it is very clear that the total magnetomotive force of the magnetic circuit is equal to the sum of each medium magnetomotive force portion within the magnetic circuit. In other words, the total magnetomotive force of this magnetic circuit will be equal to the magnetomotive force of the magnetic material plus the magnetomotive force of the air gap. The equivalent circuit of this magnetic circuit can be drawn as shown. Let's conclude this lecture at this point and we'll continue in the next lecture. Feel free to leave comments and suggestions. I am Ihsan Al-Nabi and it was a pleasure sharing this lecture with you. Thank you.